Hi students, so today we are going to start a new chapter, Electromagnetic Induction. So in moving charges and magnetism, we have studied that a current carrying conductor will produce magnetic field around it. Suppose if this is a conductor and current is moving in this direction, that is this blue cap, this is the current direction. Okay, it is moving upward. So if it is moving like this, current is moving like this, then there will be a magnetic field around this. What will be the direction of magnetic field? That we can find using right hand thumb rule. This thumb is the direction of current, so that the fingers will be curling in this direction. Okay, so current is moving in this direction, other fingers are in which direction? That is the direction of magnetic field. So if current is moving like this, then magnetic field will be in this direction. Okay, if I look like this is going to be anti-clockwise. Okay, like this. So this side it is going inside, this side it is coming like this. We have studied this. Okay, in moving charges and magnetism. So current carrying conductor produces magnetic field. Okay, so this was the observation done much before. Now Faraday, he accidentally discovered another thing. So he was doing some experiments using some circuit. So current is moving, so that was done. He noticed that a magnetic compass which is kept near to that, it was deflecting. So that was one experiment, that is current carrying conductor is making magnetic field. That was one experiment. Accidentally we got the relation between electricity and magnetism. Now this time Faraday, he discovered another thing, that is magnet which is moving or which is causing some disturbance, which is into some disturbance, is making current in the circuits. Okay, so he observed that. After that he did some experiments in order to study about this. So from there electromagnetic induction chapter starts. Okay, that is the magnet, that is magnetic field is also causing what? Current. In moving charges and magnetism we have studied that current carrying conductor is making magnetic field or producing magnetic field around it. Now here this magnetic field is producing what? Current. Okay, not directly, certain conditions are there that we will see in this chapter. So first experiment what Faraday did is, okay, first experiment. So this is a coil and it is connected to a galvanometer. So when there is no current in the galvanometer, there is no current in the circuit, galvanometer will not show any deflection. So this is like this. Okay, nothing, no problem, no deflection, nothing. This is just a closed circuit, closed loop connected to galvanometer. No battery in this circuit. Now a bar magnet, we started moving towards this. A bar magnet, we started moving towards this. So that time, that is when it is moving like this, when it started moving like this, we got deflection in the galvanometer. So as long as the magnet is coming, this was showing deflection, indicating that there is a current in the circuit. Okay, now we stopped this, we stopped moving. Now deflection also came back to the previous position, that is there is no deflection, no current. Again we started moving, there is deflection. That is when this magnet is moving, there is deflection in the galvanometer. Okay, now we brought the magnet near to it and further we cannot move, so we stopped. Again there is no deflection. So now we understood that, okay fine, this movement of this bar magnet is causing deflection, right? Now we started moving this magnet in the backward direction. Again what happened? There is deflection in the galvanometer. Okay, so movement of magnet towards the coil is producing current in the circuit. Now we did one more thing. This is north pole, this is south pole. We changed the direction of magnetic magnet. That is, we made, say for example, when north pole and south pole, if it is bringing, if deflection is in this direction, then if this is south pole and north pole, we just changed the direction of magnet, we were getting the deflection in the opposite direction. So we changed the side, deflection changed to the opposite direction. Still deflection is there, but deflection in the opposite direction. That is, the direction of current is changed. Okay, so we understood that the movement of this bar magnet to and fro, okay, north pole towards that side or south pole towards that side, it is causing deflection in the galvanometer, indicating that there is current in the circuit. When we stopped moving this magnet, current also stopped. There is no current, no deflection. We changed the side of the magnet. Instead of north pole, we brought south pole there. Again deflection started, but in the opposite direction. Again we brought it back, still deflection is there in the galvanometer. Okay, so we understood that when we are stopping the magnet, movement of magnet, no current. Some disturbance is causing this current. Okay, that was one experiment. Okay, so in this, the summary is movement of magnet towards the coil or movement of the magnet away from the coil was causing deflection. First point. When we stopped moving this magnet, current also stopped, that is there is no deflection, so there is no current. When we changed the direction of poles of the magnet, it started deflecting in the opposite direction. So 3 points. Okay, from this we got. This was the first experiment done by Faraday. Okay, next experiment. Next experiment is, okay, so here what we need to show is, suppose if this is north pole and if this is south pole, inside the magnetic field is from south pole to north pole, but outside the magnet it will be magnetic field lines will be starting from north pole. So these magnetic field lines were passing through this coil. Okay, so if the magnetic field will be passing through the coil, okay, here there is magnetic field, so this is just like a solenoid, right? Solenoid will be there, solenoid. So if there is, since there is magnetic field lines inside, this was causing current in the circuit. Okay, with the disturbance, that is, when magnet is moving, obviously the magnetic field will change. Magnetic field will increase. When it move it back, magnetic field will decrease. This increase and decrease in magnetic field is causing current here. Now here, second experiment, same setup. Okay, same setup. A coil with a galvanometer. Just like this case, here also no battery, so no current. Now we made a current carrying loop on one side. We just replaced the magnet with a current carrying loop. Suppose if this is coil 1, this is also coil 1, this is coil 2. So this coil 2 is carrying current in the circuit, and current carrying coil will produce what? Current carrying coil will produce magnetic field. So if current is flowing in this direction, the obviously magnetic field will be there in this direction. Around, if current is Current is moving in this direction, magnetic field will be there. Current is moving in this direction, magnetic field will be there. Current is moving in this direction, magnetic field will be there. Okay, so here this is producing magnetic field. So we replaced the magnet with a current carrying conductor. Obviously we have studied in moving charges and magnetism, current carrying conductor will produce what? Magnetic field. Okay, so we started moving this coil to and fro. We started moving this coil to and fro. So this current carrying coil, if it is moving in this direction, okay, when it is moving in this direction, we were getting deflection in one direction. When this current carrying coil it is moving in the opposite direction, we were getting deflection in the opposite direction. Okay, so previously we used real bar magnet and we saw deflection. Now this time a current carrying coil which is acting as a bar magnet, okay, it will act as a bar magnet because this is also making what? Magnetic field. So when current is flowing in this, this is what? Just like solenoid, this is also solenoid. What will happen? There will be magnetic field inside the solenoid. So we can think that, okay, we can understand that magnetic field is inside the solenoid. So here, since it is carrying current, what is happening? This is producing magnetic field. So this coil, when we make to and fro motion, there is deflection in the galvanometer. So a current carrying conductor, when it is moving towards or away from a coil, what is happening? Current is induced here. No battery, nothing is there, but movement of this is making current here. Okay, so this phenomenon is called induction. We will get into that in detail. Now here the necessary of bar magnet is not the absolute necessity. We just need a current carrying conductor which is enough to make current in the coil. Okay, so this is the second experiment we understood. Okay, current carrying, the movement of current carrying coil, okay, that is also creating magnetic field. Actually they have done one more thing. They kept this as stationary. They tried to move this also. Okay, another point is the first one, this was made stationary, this was moving. Then they made this one as stationary and they started moving this. Again, in all these cases, what happened? There is deflection in the galvanometer. We understood that current is there in the circuit. So first experiment was like a movement of magnet to and fro was causing current in the circuit. Second experiment taught us like a relative movement of coils creating magnetic field in the first coil, primary coil. Okay, the coil where battery is not connected. Okay, when there is movement of this one, definitely there will be some current induction in this also. Okay, that will be there. We will study all that. Okay, but now these experiments are just showing that current is induced or current is made to produce in the coil if we move bar magnet towards it or away from it, or two coils, relative movement of two coils is causing current in the circuit. Okay, this is the second experiment. So here two cases can be seen. This is first case, this is stationary, this is moving. Okay, second case is stationary and this is moving, and second case this is moving and this is stationary. Okay, so this was also causing what? Current induction. Clear? So while these two are moving, suppose, okay, shall I erase this? You note it down. Okay, please note it down. Note the points also. Okay, note the points also. Okay. Suppose if both are moving, okay, suppose if this is the coil, here galvanometer, and this is another coil, and here we have connected a battery. Suppose if we do like this, if this is moving at 5 meter per second, this is also moving at 5 meter per second, will there be current in this coil? Will there be current in this coil? What do you think? Both are moving with 5 meter per second. Will there be current in this coil? Okay, what do you feel? Okay, no. Okay, current will be 0 because there is no relative movement. Okay, there is no relative movement. If this is moving at 5 meter per second, if this is moving at 6 meter per second, if there is some relative movement, definitely there will be current. Okay, that also you can understand along with this. Third experiment. So third experiment is, okay, this is galvanometer. Here we are not going to move anything. What we are doing is, there is a switch here. There is a switch here. We will just switch on, tuck. There will be galvanometer deflection, tuck. Then we switch up, just like a galvanometer will show deflection, immediately it will come back to previous position, because sorry, when we switch on, tuck, so there is some disturbance, but after doing this tuck, that is switch on, there is no disturbance. So current will form in the first coil, that is this one is coil 1, this is coil 2. Current will be there, okay, for an instant, then current will vanish because no disturbance here. So again, okay, we are switching on, tuck, deflection, tuck, tuck. It will show deflection, again it will come back to the previous position. Then we switch it off, tuck, tuck. Understood? We switch on, galvanometer deflection, tuck, tuck. When we switch off, galvanometer deflection, tuck, tuck. So again, if you switch on and if you keep on switch on, we don't do any difference. There is galvanometer deflection, tuck, tuck. Then after that there is no deflection. When we switch off, immediately tuck, galvanometer will show deflection, tuck, tuck. Okay, so either switch on, switch off, there is no deflection. Switch on, off, on, off, on, off, there will be deflection. Okay, so someone is playing tuck, 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 galvanometer will show deflection. Okay, so that disturbance is important. Okay, just current or movement, that is not enough. Okay, there should be relative motion or there should be a difference. Okay, we will get into this in detail. So we understood that relative movement is also not the absolute necessity. What we need some disturbance. So here this is also not moving, this is also not moving. We are just switching on, off, on, off, on, off. What is happening here? When we switch on, magnetic field will increase. Okay, this one, this switch on, galvanometer is showing deflection. Why? Because when current is there, what is happening? Magnetic field will be in this coil, so that will be shared here also, so this will create current here. Okay, now when we switch off, galvanometer show deflection in the opposite direction. Switch on continuously or switch off continuously, no current, no deflection. Clear? Okay, so 3 experiments. First experiment is just movement of bar magnet to and fro, causing deflection. North pole is coming, deflection to one direction. South pole is coming, deflection to the opposite direction. then a current carrying coil, we are bringing towards the coil, there is deflection in the galvanometer. In coil 1, it is moving away, deflection in the galvanometer in the opposite direction. Now here, no movement, just switching on, deflection in the galvanometer, switching off, deflection in the galvanometer. If we keep on switching on, then there is no deflection. If we keep it switching off mode continuously, there is no deflection in the galvanometer. So not this thing also. Okay students, so we have seen 3 experiments. Based on that 3 experiments, Faraday gave 2 laws. Okay, Faraday's laws. Okay, so we will move to those statements. Before that, we need to understand certain things. We have seen a phenomenon, okay, by just understanding those experiments. Now why all these things are happening? What are the details of that? Why current is deflecting? What is the real reason when it is moving, current deflection, when it is moving away, current is deflecting in the opposite direction? Why is it so? Okay, all these things we will analyze. So for that, we need to understand certain things. One among them is magnetic flux. You have already studied about electric flux. What is electric flux? The field lines passing through an area. Okay, the field lines. Which field lines? Electric field lines passing through an area is called electric flux. Okay, suppose if this is area, through this area, how much electric flux is passing? Okay, that is what is electric flux. Electric flux, how much field lines are passing, that is what is electric flux. So what we do, electric field lines passing per unit area means divide by A. Passing through unit area means into A. Okay, if area is bigger, the field lines passing also will be more. Okay, area is less, the field lines passing also will be less likewise. Okay, per area, per unit volume, per area means divide we used to do, but passing through an area means we will have to multiply. Now, so magnetic flux is what? Just same thing like electric field lines passing through an area. Here the only difference is here magnetic field lines, nothing else. So magnetic flux through any surface placed in the placed in a magnetic field. Okay, so this is magnetic field. Placed in a magnetic field is the total number of magnetic field lines crossing the surface normally. Say for example, if this is the magnetic field lines are going, maybe here we might have kept a north of a magnet, here south of the magnet. What will happen? Magnetic field lines will be passing. So magnetic field lines are passing. On the magnetic field lines we kept a surface area like this. So how much is this area? Magnetic field into that much area will be what? Magnetic flux. Suppose if we tilt at an angle, okay, then how much area vector or how much component of area is there in this direction, in the normal direction, that into magnetic field will be the magnetic flux. I will show you here. First thing, already you might have studied what is area. Area is a vector or scalar. Area is a vector. Suppose if we consider this such an area, this is area, and what is the direction of area vector? Area's direction will be normal towards it. So we can take either in this direction or this direction, it's our wish. But suppose in a problem or in a case, if we have considered area in this direction, then till the process ends or till the problem ends, we should consider this direction itself. In between we should not take this one or this one, we should not change. Okay, so any area normal to that will be the direction of that area vector. So here if the area is kept like this, okay, just like this, if this is the direction of magnetic field, if this is the direction of magnetic field, area is kept like this. So this is the direction of area, correct? This will be the direction of area. This is kept like this. And which direction magnetic field is going? Magnetic field is going like this, and this is the direction of area vector. This is the angle between them. So I can put angle theta. So I repeat, magnetic flux is the number of flux lines. Okay, magnetic flux through a surface is the magnetic field lines passing through an area. So perpendicular, okay, that is to the surface normally. Suppose if this is the surface, magnetic field is this, moving in this direction, then this area into magnetic field. Suppose if the area is like this, area is like this, area is like this, then this is the direction of area, and this is the direction of magnetic field, means theta is the angle between magnetic field and area vector. Theta is the angle between magnetic field and area vector, right? Now area is a vector, okay, area is a vector. What about magnetic field? Magnetic field is also a vector, okay. So we have studied in vector algebra, a vector and vector, a normal multiplication is not possible. Either we will have to do dot product or we will have to do cross product. If we do cross product, the result will be vector. If we do dot product, the result will be scalar. So based on the result, we will be able to say that whether dot product or cross product we need to do. So this magnetic flux, this is actually a scalar. So magnetic field B is a vector, area is also a vector, and this is a scalar. So what we should do here, what operator we can do here? Nothing but dot product. So phi B is equal to, if we expand this, this is nothing but magnitude of magnetic field into magnitude of area into cos theta, where theta is angle between magnetic field vector and area vector. So that is why we have taken this example, this area is inclined. Okay, so that time how we should apply. So this is the formula for magnetic flux. Okay, note down these details, we will investigate further. Suppose if we have some area like this and magnetic field is passing like this, and area is an irregular area, okay, so that time this magnetic field is also not uniform, okay, it will not cross actually, okay, magnetic field is not uniform, okay, magnetic field is not uniform. Suppose if we consider an area like this, say this is dA, and a magnetic field is passing through this, okay, magnetic field is passing through this, then we can say that the small magnetic flux passing through this small area dA will be what? B dot dA, B dot dA. Suppose if we need to find the magnetic flux through the full area, the total magnetic flux, means we will have to add all these magnetic flux d phi. So this is going to be B dot dA, integral B dot dA. So if it is a area, big area, and if this magnetic field is not uniform, if it is changing, then what we will have to do in order to find the total flux, we will have to integrate. So this is also a formula. Magnetic flux is equal to integral BDA. So this is also we can note down. So magnetic flux is equal to B dot A, which is BA cos theta. So suppose if theta is equal to 0 degree, 0 degree means suppose magnetic field is in this direction and we keep an area vector in this direction. So here the angle between this is magnetic field, this is area vector. Just like this is the magnetic field is in this direction, area is also kept like this. So this is area vector. At the same time magnetic field is also in the same direction. So in that case theta is equal to 0. We could say that phi is equal to BA cos 0. So phi will be what? BA. So this is the maximum flux possible, maximum flux value possible. Okay, maximum value of cos theta is what? 1. So that is possible when the area vector and magnetic field vector both are in the same direction. Now another case is theta is equal to 90 degree. Theta is equal to 90 degree means if this is magnetic field and we have kept the area like this, we have kept the area like this. So if we take the area vector in this direction, that is coming out, so I am putting a dot. So this is the magnetic field direction, this is the area direction. What is the angle between area and the magnetic field vector? Suppose if this is magnetic field vector, if the area is like this, then area vector will be towards the normal. So this will be the direction of area vector. Okay, you can see. Okay, this will be the direction of towards you. Direction of area vector, this is magnetic field vector. The angle between them is 90 degree. Angle between them is 90 degree. So if this is the magnetic field vector, I can say that I cannot show, but I will write here 90 degree. So theta is equal to 90 degree. Phi is equal to BA cos 90. Cos 90 is 0. So phi will be having minimum value, which is nothing but 0. Another case is theta is equal to what? 180 degree. That is this magnetic field direction is this, area vector is that direction. So this is the area vector. Area vector will be in this direction. Magnetic field will be flowing like this. Direction of magnetic field will be like this. So 180 degree will be the angle between them, and so we can write phi is equal to again cos 180. So the phi, the value of the magnitude of phi max is how much? BA. Negative will come, but that doesn't matter here. Okay, so that also will have maximum value. Okay, doesn't matter. So even if we take area vector in this direction or this direction, it is not going to affect the magnitude value. Okay, clear? Suppose if the theta value is less than 90 degree, if the theta value is less than 90 degree, then cos theta will be positive. Cos theta will be positive, and so phi value also will be positive. See, 90 degree means 0 to 90 degree. Less than 90 degree means first quadrant. So here all are positive. Cos, sin, tan, everything will be positive. So cos theta will be positive. When theta is less than greater than 90 degree, greater than 90 degree, cos theta will be negative. Suppose if we get a value here, this will be, cos will be negative here. Okay, only sin will be positive here, so cos will be negative. So phi will have negative value. So note it down. We'll see a few more details about fundamental details about magnetic flux. See, unit of magnetic flux, dimensional formula, all that. So magnetic flux. So its unit is, so magnetic flux is nothing but B cross B dot A, magnetic field dot area vector. So what is the unit of magnetic field? Okay, that into meter square we can take. Okay, so what is the unit of magnetic field? Tesla, area vector, so Tesla meter square. So this is what is the unit of magnetic flux. This putting together, all these things putting together, we call Weber. Okay, this is both are SI units. Okay, SI unit. So generally we say Weber. Weber is the unit of magnetic flux. Now another unit is also there, Maxwell. Maxwell is also a unit for magnetic flux. So this is like just like 1 Tesla meter square is 10 Maxwells. 10 raised to 8 Maxwell. 10 raised to 8 Maxwell. 1 Tesla meter square is equal to 10 raised to 8 Maxwell, same as 1 Weber. Okay, so this is its unit. Okay, now we will see the dimensional formula of magnetic flux. So dimensional formula, phi is equal to B dot A. So dimensional formula, asking dimensional formula is important. Okay, they will take anything and they will ask what is the dimensional formula of this. This is very important. So we cannot remember all the dimensional formulas. We should not do that. Okay, certain things by practice it will go into memory, that is fine. Other ones very fastly we will have to take it from the formula or units. So here, so pause the screen and try to find the dimensional formula of flux, magnetic flux. Okay, then verify here. So phi is equal to B dot A. So B, how to find the dimensional formula of B? In moving charges and magnetism we have studied this formula, right? Q into V cross B is equal to F force. So QVB is equal to F, sin theta is there. So magnetic field B is equal to F by Q, F by Q V, F by QV. So flux is equal to F by QV into area. So dimensional formula of force is MLT raised to minus 2. Dimensional formula of charge is AT. Coulomb is not fundamental unit, ampere is fundamental unit. So into LT raised to minus 1 into L square. Okay, fine. Now we will take from this and this will be cancelled. T raised to minus 1 will be cancelled off. So ML square T raised to minus 2 A raised to minus 1. So this is the dimensional formula of magnetic flux phi. Clear? Now how this flux can be changed? Okay, flux can be changed by changing magnetic field. Phi is equal to BA cos theta, BA cos theta. So magnetic flux can be changed by changing this magnetic field B or area or this theta, the angle. Suppose if this is a coil and coil means this is area and this is the magnetic flux. If we change this magnetic field, if we change this magnetic field, just say for example B is equal to 2T square, that is when time T is equal to 0 magnetic field is 2, when time T is equal to 1 magnetic field is 2. Okay, when time is equal to 0 magnetic field is 0, when time T is equal to 1 magnetic field is 2. or when time t is equal to 2, magnetic field will be 2 into 4. Likewise it is changing, keep on increasing. So that time also what will happen, this magnetic flux okay, linked with this loop will be increasing. What is this area? Area is the area of the loop or area of the coil. Okay, area of the coil or area of the loop. So this is one way, okay, by changing magnetic field. Okay, another possibility is suppose if this is magnetic field, if this is the loop. So suppose if there is any method to increase the size of the loop, just like this. Suppose if this is radius, okay, this was the previous radius, now this is the radius. So if area is changing, when area is changing, what will happen? Magnetic flux will change. That is one method. Third method is what? Suppose if this is magnetic field, we have kept a coil here, and this coil we are rotating at some angular velocity. So now the magnetic field is going inside. So if area is this, and if I consider the area vector towards inside, magnetic field, area vector, both are in 0 degree. Now if I rotate this coil, then magnetic field is going inside still, but area vector is in this direction. The angle between magnetic field and area vector is 90 degree. Now again if I turn the coil, magnetic field is going inside, area vector is in this direction, angle between them is 180. Now if the coil rotates like this, 270 degree, again 0 degree. So if it rotates, this theta will change. Still what will happen? This magnetic flux will change. Okay, so these are the methods to change the magnetic flux. Suppose again, if this is magnetic field, if we have a coil and this coil is moving with a constant velocity v, so if this coil moves out of the magnetic field, again what will happen? Flux will change because area is decreasing, right? When it is coming into the magnetic field, area will increase. Again if it goes out, area will decrease, okay, with respect to this magnetic field. So these are all the ways to change the magnetic flux. Okay, please note these things also. Now let us see Faraday's first law and second law. So Faraday's first law, whenever magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit. The induced EMF lasts as long as the change in magnetic flux continues. Okay, I read the statement again. Whenever magnetic flux linked with a closed circuit changes, an EMF is induced in the circuit. Okay, so we have seen in the experiments magnetic bar, if it is bringing towards the coil, current was there. The reason for current is EMF. When it is moved away, again current is formed. A current carrying coil also we brought near, again current formed in the closed circuit. Again two coils, one coil current is switched on, switched off, again still current is formed in this coil. Okay, why the current is formed? Because EMF is created. What is the reason of this EMF? That is what Faraday is saying here. The magnetic flux linked with a closed circuit, the magnetic flux linked with a closed circuit changes. So this is the reason for the EMF. If the magnetic flux linked with the circuit changes, EMF will be induced. And as long as that induced EMF will be there as long as the change in magnetic flux continues. So change in magnetic flux continues, then EMF will be there. If change in magnetic flux stops, EMF also will become zero. So when the magnetic bar is moved to and fro, the change in magnetic flux is continuing. See, magnetic bar, a magnetic bar is bringing towards the closed circuit. This coil is closed circuit. If it is broad, it is coming. Magnetic bar is coming. Magnetic bar is coming means magnetic field is increasing. Magnetic field is increasing means what is magnetic flux? B dot A. B dot A is increasing. When B is increasing, B dot A is increasing. So magnetic flux is increasing means that is a change in magnetic flux. Magnetic flux was 0, then magnetic flux became 10 Webers. It is changing. EMF will be induced. Now this magnetic bar is moving away. Magnetic field is coming down. When B is coming down, B dot A is coming down. Magnetic flux is coming down. Again EMF will be induced. So change in the magnetic flux is the main reason for induced EMF. Okay, so change in magnetic flux. What about Faraday's second law? The magnitude of induced EMF in a closed circuit is directly proportional to rate of change of magnetic flux linked in the circuit. What is the EMF? How much EMF will be produced? That is what Faraday's second law is discussing. The magnitude of EMF induced in a closed circuit is directly proportional to the magnitude of EMF induced. The magnitude of EMF induced is directly proportional to rate of change of magnetic flux. Rate of change of magnetic flux. Clear? So we'll write here the EMF induced E. Okay, let's consider its magnitude only. We will be considering now. This is equal to the rate of change of magnetic flux. This is change of magnetic flux. If we write by delta T, this is nothing but rate of change of magnetic flux. Clear? Rate of change of magnetic flux. Right? Now if we need instantaneous value, okay, for a particular instant, what we will do? This E is going to be d phi by dt. Okay, just the magnitude, that is just the value. Clear? Understood? Note it down. So E is equal to, that is the value, the magnitude is either delta phi or change in magnetic flux in the time duration, or we can write this as d phi by dt. But honestly speaking, without considering the magnitude, if we write it directly, this is nothing but minus delta phi by delta t, or we can say minus d phi by dt. Okay, so why this minus comes? Next topic, that is Lenz's law, is analyzing this negative in much detailed way. Okay, complete Lenz's law and its problems, okay, are related to the direction of this induced EMF, direction of current flow, etc. Okay, so we are not discussing much about this negative. I'll be telling the reason for this negative. Actually, this EMF is induced in order to oppose that change. What change? Flux will be increasing or decreasing, right? Already flux is there. Okay, peaceful, no problem. Okay, but if it is suddenly increasing, the system will try to decrease it. If it tries to decrease it, the system will try to increase it. That is, anyone, everyone, you as well as me, or the whole universe doesn't like changes. Okay, we don't like changes. Just like inertia. Just like inertia. If it is at rest, it is comfortable at rest, it doesn't want to move. Okay, so inertia of rest is there, inertia of direction, inertia of motion. If it is in motion, suddenly it doesn't want to stop. So everything will oppose the change. Same thing here. Okay, when flux is increasing, it will try to oppose that flux. So in order to oppose the flux, this EMF will be induced. That is why the direction of induced EMF will be a negative to the already existing one. That is why we are putting a negative. So about this negative, about the direction of EMF, about the direction of current, all these things we will discuss in the next topic. Right now, the main thing which we need to understand now is EMF induced is the reason for current flow. EMF is induced just because of flux change. How much is the EMF induced is nothing but the rate of change of magnetic flux. Okay, so E is equal to minus, no need to look at the minus now. You can concentrate here, delta phi by delta t, or d phi by dt, or simply we can say EMF is equal to average EMF. Okay, average EMF is equal to final flux minus initial flux divided by time duration, or instantaneous EMF is nothing but d phi by dt. Okay, please understand this. Okay, fine students. So today just introduction of the chapter. What is Faraday's experiments? 3 experiments we have seen. Then what is magnetic flux? Without understanding magnetic flux, this chapter cannot be studied. After studying magnetic flux, okay, we have seen how this magnetic flux will change just by changing the magnetic field, or just by changing the area, or just by changing the orientation of the loop. Okay, that is the angle between loop and magnetic field. Okay, so area vector phi is equal to B dot A. Now we have seen the Faraday's first law and second law. First law says that EMF is induced just because of change in magnetic flux. Second law says the magnitude of induced EMF. So induced EMF is nothing but rate of change of magnetic flux. Okay, so in the next session we will look at the problems. Okay, just we will see the problems, how to find the change in magnetic flux, how to find magnetic flux. Okay, varieties of problems we will see in the next session. Just revise this, study this, and attend the next session. Thank you children. Bye bye. Good luck.